Information. Obvious goal is to extract information from a data set. We're going to be looking at predictive modeling. We've seen big data is complex, high volume, high variety, high velocity, requires pre-processing, feature engineering, and nearest neighbors. But ultimately, we want to get information, and we'll get that from predictive models. Let's take the long view in this video. We're going to actually introduce the next three videos: information surprisal, information entropy, maximum entropy principle, and information. And we're going to do so in a context which mixes a summary of what we've done so far with a suggestion of where we're going. We've seen high volume, but we don't study big data just because there's a lot of it. And we don't study big data just because it needs to be collected and stored. These are very, very important issues and attributes of big data. But we study big data because of high variety. Big data is complex, and that makes it information rich. There tends to be a great, huge amount of very good information in big data that actually spans often across multiple scales. So the goal is information, the underlying structure, etc. And we can do this even when the data is unstructured. So structured data is what we've been working with: observations and features, and then we have some responses. And the only response we've really talked about is class, but that's just one possible response. There may be tables of tables of tables, but unstructured data has associations instead of tables. We often see the observations as key value pairs, or in general as pairs of things together. We may have a word on a page and a count of the number of times it occurs, a socialite in a Facebook network, and a friend of that socialite. So you can see that this implies networks. Associations or similarities are the edges. And this works for both structured and unstructured, as we've already seen. Here is an example: some unstructured data that came from Twitter during the Super Bowl, looking at hashtags. And so you can see the size of the vertices is the number of times these hashtags were used relative to all of them. And the colors have meaning with respect to the teams. And there's a lot of interesting information here. GoDaddy and Esurance and J.C. Penney was kind of a surprise there for me. Nearest neighbor networks are very intuitive, and that previous slide shows it. We just simply had to look at the network and kind of see what's going on. We tend to have graphs where vertices are observations and edges are similarities between observations. But for unstructured, that could be collections of values, and the edges would be defined by the key value pairs, for instance. Predictions are based on nearest neighbors. We find observations with similar features, and then the prediction is constructed from their responses. Nearest neighbor approaches are fundamental. They are the long running basis for pattern recognition in artificial intelligence, and they can model these complex underlying structures. Let's look at an example. Suppose we wanted to classify iris data. That's three classes, and just using two features, the sepal length and the sepal width. We could use neighbors to predict the class of an unlabeled point. Notice we're using red, green, blue as the colorings for the classes. So I've got a point here which is surrounded by red, so therefore I would predict that it's red. I've got a point here surrounded by blues, so I'd predict that there's blue. Now I can actually set up a grid on the entire plane, make it very fine, and then do this for every single one of the points in the grid, and I get this kind of a picture. And in this picture we have what are called decision boundaries, which separate what we predict is red from green from blue. But there are issues. So what about a point that's sort of on one of the boundaries? Is it blue or red or green, or can we say anything? So in general, nearest networks, neighbor networks have issues. There's not always the same K. We're going to have to do feature engineering. Some features are going to be more important than others. The actual criteria for closeness could be incredibly complex. Why are two people friends in a social network? That might be a very, very complex question to answer. And predictions using nearest neighbors can be misleading, as we just saw. But we can fix this one. So let's do so. So instead of predicting the class, we're going to use neighbors to predict the probability that a point is in a given class. So we're going to have three probabilities: probability of red, green, or blue, uh, probability for a point being red is a likelihood, a confidence of it being in the class Setosa, which is red. Neighbors can predict these probabilities for each point. So for instance, if I have this original point surrounded by red, no surprise that we might predict that that has 1 for red and 0 for blue and green, and we'd color it red. In the same way, we've got red, green, blue. Blue is last, so that's 0, 0, 1 for this point surrounded by blue. No surprise, we predicted it's blue. And this gives us what's called a predictive model. Notice that we have areas that are represented by white that where we don't have a real indication of which color we should assign. And the colors are lighter in areas where we're less confident that that is the color it should be assigned. In particular, some of the points don't have any definite color. That point we looked at last time in our predictive model doesn't have a color. In other words, sometimes we don't know, and our models should reflect that. So how do we do predictions with probability models? Well, suppose we've got y associated with a set. A model is any distribution, q of y, on that set. So q of y greater or equal to 0 and the sum of the q's is equal to 1. Any function that does that is a model. Uniform, if we have m outcomes, 1 over m for every outcome. A point distribution, where we have 1 for one of the outcomes and 0 for all the rest. And of course, a true distribution is also a model. In fact, it's the best possible model, and it's our goal. So how do we get this best probability distribution? Well, first off, we notice that probability is a property of the process that produces the data, not the data itself. Probability is defined by a limit. So we can only estimate the true probability distribution from a given set of data. See, the data is size n, but n is not going to infinity. It's fixed. N could be incredibly large, but it's still not infinity. So given a data set, our goal is to find a probability distribution that best approximates the true distribution. And we can do this using a moment problem. So if we could find a approximation that estimates the true distribution, then we would get the same expected values from both. So let's review just quickly about averages and expectations. So if we have a function, a variable associated with sample space, the average value of the function over a collection of trials, a finite set of trials, is just the average. But if you have infinitely many trials, and notice my emphasis here on infinitely many, I've got the dot 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 there. So that's the ellipsis. That means it goes on forever. The expected value is the limit as n goes to infinity of 1 over n, I equals 1 to n, f of y sub I. And this expected value is independent of any single data set. So what if I just threw out the odd index trials? Well, what happens to the expected value? Nothing. It stays the same. So expected value is a property of a process not a data set. Now let me remind you some things. So how to define a probability. Remember, these are the counts, C sub n of O sub y, the number of times that outcome y occurs in n trials. I'm going to use some notation in just a minute. I sub y sub 1 up to I sub y sub r means that there are r trials in which outcome O sub y occurs. So let's look at expected value of f of y. This is a limit of average values of f of y sub I. And I'm going to write it expanded like this. That's what the summation notation means. And now I'm going to regroup. Everything where the y sub I is a t1, I'm going to put at first. Where it's a t sub y, I'm going to put that in the yth position, and so on and so forth. So because all of those y's are the same outcome, then I can just take f of t1 and multiply times the counts of outcome 1, all the way up to f of ty times the counts of outcome y, and so on. But now I take the limit of the counts over n, and I get probabilities. So the expected value of f of y is the sum y equals 1 to m of f of t sub y, the probability of y. So let's look at the moment problem. If I've got a model on a sample space, then the q expected value of f of y is just simply the expected value where I'm using q of y in place of the actual probabilities. So it's a probability distribution. This is an expected value, and so I call it a q expected value. Now if the expected values were the same for all functions, then q would have to be the true distribution. But this problem is all but impossible to solve. Even if we only consider functions of this form, f of t equals t to the k for positive integers k, it's really very, very difficult to solve this problem. So instead, let's see if we can find something we can solve. Now, an empirical distribution, when we have n trials producing outcomes y1 to yn, and remember y here is referring to a class, or more generally response. Now we actually have with every trial several features in association with the response, and we can use the features to get the best model for y, and we'll do that. But for right now, we're just going to look at y and its empirical distribution. It's just what you get when you take the counts divided by n. Now n here is not going to infinity, so this is not a probability. It's only a model that we call the empirical distribution for a fixed large capital N. So the maximum likelihood principle says that for a given data set, as samples of a variable y, the log likelihood function of a model q is this sum of the empirical distribution of y times the log of qy. And this log, by the way, can be any base. So natural log, log base 2, log base 10, doesn't matter. The model p sub y that maximizes the log likelihood function is closest to be true. This is the maximum likelihood principle. This is as n goes to infinity. And what that says is if the log likelihood of p is greater than the log likelihood of q for all models q, then p is approximately the same as the true distribution, and it becomes exact as n goes to infinity. But we want to go beyond maximum likelihood. We'll want to use feature engineering, multiple models, and so on, more than empirical distributions, and we'll even move beyond probability itself. So we're going to be looking at a new definition. If q of y is a model for a variable y associated with this set, the information entropy is h of q is negative sum y equals 1 to n q of y log of qy. And notice that looks an awful lot like the log likelihood, this information entropy. So we're going to be seeing the maximum entropy principle, which says that the probability distribution which best represents the current state of knowledge is the one with the largest entropy. Now, what do we mean by entropy? Well, entropy here we're thinking about is uncertainty about what the data does not explain. So uncertainty is a type of information. In particular, uncertainty is information that we don't have. It's information we could have, and if we had it, we would know more, but we don't have it, so we have uncertainty. Now, maximum entropy and maximum likelihood are equivalent in a large number of cases. In particular, the traditional statistical modeling approach of a parameterized family of distributions, maximum entropy and maximum likelihood are equivalent. So information and entropy. We're going to be doing predictive modeling, given a data set, finding a model P of y that best predicts responses. The one the data implies is closest to P true is the one that we're hoping to get. And it's going to be the one which maximizes the uncertainty, the information not explained by the data. So decision boundary models are simple examples, but we're going to try to be more sophisticated. But of course, at this point, what we really need is we need more information about more information, which is what the next 3 videos are going to give us.